So before we start with the next speaker, so you already heard that Merck is one of the largest pharmaceutical companies in the world, and their headquarters is in Darmstadt. I think more than half of Darmstadt belongs to Merck. Okay, maybe not. We had a wonderful talk by two Merck data scientists or data analysts. And actually, it was disappointed to me. You can give such a nice talk, but you don't want to do research. You don't want to do your PhD. The role model is staying in front of you. And this is why we start. It's a mistake not to do PhD when you are such a smart person. Then we start with Dr. Hannah Bürckstümmer. It's a completely different topic than security. This is what we wanted. She did her PhD in chemistry. That's really interesting. And then she started to work on organic solar cells. She did her PhD in University of Würzburg. We have also Alexandra from University of Würzburg, so you can make friends. Then she joined Merck since 2011. And now she's working on neuromorphic computing that is actually a big thing, especially also in security community. It's a big thing, and I'm really looking forward to her talk. She's innovation manager. She has done leading positions, research positions, so it's very exciting to hear her experience. Thank you.
Thank you very much for the introduction and the opportunity to talk here. So I missed the talk of my colleagues, unfortunately, so we will catch up later on about that. Maybe the technology is working and we stay at the slides I want to see and not switching back and forth. So I'm looking forward to share the next minutes with you what the Innovation Center at Merck is doing, because we get this question all the time inside of Merck, but also outside. What are you doing in this fascinating glass building there? And next I will share what neuromorphic systems are, why we think they are important, why we have chosen that as a topic. And then I will end with a personal note. So, neuromorphic systems at the Innovation Center in Merck. Okay, it's not switching here, doesn't matter. So this is showing what the Innovation Center in Merck is doing. So we have heard in the morning, you have heard in the morning, we have three sectors: healthcare, life science, and performance materials. And in the Innovation Center, we are trying to build up business either beyond these sectors or between. So beyond could mean a new market, could mean something which is out of the timeline of the sector, and between could mean we can combine technology from healthcare with something in life science and bring new business. So this is what we are, what our mission is in the Innovation Center. And how do we do that? So we have a strategic framework in the Innovation Center. These are interest fields such as innovation fields, what you see in the lower left in the yellow part. And this is basically the roof. And under this roof, we are trying to find ideas. We have different channels. We have internal ideation channels and programs. InnoSpire, for example, is one of them. Every 2 years, it's run. This year, we had 400 ideas coming in, and then they are selected, and some of them win and continue. Idea concepts or idea projects which are successful are matured into innovation projects, which are then hosted in the Innovation Center for several years to really bring business in that area. We also collaborate a lot with externals, of course, because we are not the only bright minds. We know that there are many, many people outside which can complement our capabilities. Today, we have several innovation fields running, and I want to show two of them. Clean meat is one of them. So it's about cell-cultured meat, and this is very close to our life science business because they are doing the media for cell culturing. They are also doing the cell lines. So here, in this innovation field, people are trying to advance that field. So at some point, people can eat meat without any animals involved, or at least only a little bit, because you need the stem cells in the beginning still, but that's the only thing you need from an animal, and everything else is basically done in a petri dish with much less water, land, energy use than you have if you have the animal on the in the outside. Another topic is liquid biopsy technology. So how can we use our blood, maybe also our breath and saliva, to know more about the illnesses which people might have or the progress of an illness? So one field which is quite advanced is prenatal diagnostics. So you can now from the blood get a lot of diagnostics about the baby, and there are many other illnesses where you can use this technology to get early information or much more information than with other biopsy technologies. But now we are talking about a different topic here today related to cybersecurity and artificial intelligence, and this is one of the 2 new fields we have endorsed end of last year, so it's totally fresh and new also inside our company. We have decided that bioelectronics and neuromorphic systems are 2 intrinsically attractive areas which are very related to Merck and where we think we can make a contribution. And now let's jump to neuromorphic systems. So what is it first? What is a neuromorphic system? It's a system trying to emulate the working principles of our brain. What does emulate mean? So simulate, emulate, somehow it's the same. Simulation is if you do something in software, and emulation means you try to bring into a physical environment what our brain is doing. So the chip itself has the same working principles as our brain. I will show you in a minute how this can be done. But first, maybe let's ask the question, why do you want to do that? Why? So it's rather impressive what our brain is able to do. So on the left side you have the brain, on the right side you have the IBM Supercomputer, and when you compare the computing power of both, our brain is superior in the operations per second. It equates to 5 to 6 IBM supercomputers, which is in itself very impressive, I think. But if you look at these numbers running now, our brain can do that at 20 watt, and one IBM supercomputer is 65 megawatt. Process that with your amazing brain and get impressed, because we have such an efficient thing up here. We're not really using everything of that, but and to get a little bit of that into a computer chip would do amazing things, and I will share a bit about that later on. So why do we care about this efficiency? Why don't have IBM supercomputers everywhere? That's because of the efficiency. It's a bit slow. So how much energy does it cost us to do all this data processing? You see on the left side a typical Google search, and you see on the left side kind of an equivalent. So if you do 220 Google searches a day, it equivalents to boiling 1 liter of water. So maybe this doesn't mean a lot to you because you have a water kettle and you just press a button and that's it. But there are other areas where you have to collect the wood and maybe there is not enough wood. So it's really quite a lot of energy. And if you sum this up currently, our information and communication technology adds up to 10% of our global energy use. 10%. And there is a lot of assumptions, how much is it growing? So in this figure you see 2030 up to 20%. So now when we think about carbon usage, about climate change, so this is really an issue we have to take care about. And actually, it's very interesting that at the moment we have this Flugscham, you may know that, because there's so much carbon dioxide going into the airplane industry. This industry is doing the same range of carbon dioxide emissions. So maybe in future we will have digital shame. Let's see. We are trying to do something about it before we are going into that. And so for me personally, the sustainability topic is very important. But as you know, in industry, money is more interesting. So this is something which will come later, I think. But at the moment, the more pressing need or the more pressing is what can you do with these systems which are similar to our brain? And here there is one part of this digital and information technology which is getting more and more interest, and this is called the edge. So the edge is basically where the data is generated, all the Internet of Things, sensors, your mobile phones, or airplanes, for example, terabyte of data every day, or security cameras, even exabyte of data if you can process these numbers. And also interesting, I think, is the last point, if everybody of us would use his voice assistant 3 minutes a day, we would have to double the data centers in the world. And when you think back to the energy use, So yeah, there's a lot of data being generated. People even call it a data explosion because all these sensors are multiplying. So wouldn't it be cool to process this data at the point of origin and not sending everything to the cloud with all the problems related? And this is where neuromorphic systems can really add to the value of things, add then to the market share of companies, and then it gets interesting. And this is where the industry is currently looking at. For example, when you think at autonomous driving, there's a lot of sensors there and a lot of data processed. If everything has to be communicated with the cloud, you have a latency problem. You have a bandwidth problem. And what you also have is if you want to process everything in the car, you need a very potent chip, which needs a lot of energy. And if this car is driven by a battery, then you have a competition. How much energy the chip gets, how much energy you have for the range. So to have a highly efficient computer chip, for example, a neuromorphic one built in an autonomous car would add a lot of value and advance the autonomous driving industry towards level 5. Internet of Things sensors, there obviously, if you think about production, reliability is a real topic. What happens if there's no connection anymore between the sensor and the network? That would be a real problem. Bandwidth is a problem, and battery. These things are small. You cannot have a lot of battery in there. So if you have a highly efficient chip, not using a lot of battery power, this would be really a selling point. Smartphones, also interesting, and then related to the security topic. Wouldn't it be cool if our phones would do most of the processing just at the phone without connecting too much to the cloud? Also data storage. What if the chips would be so strong in computing power, but on the same time not using a lot of battery energy, and they do everything on the phone, or most of that. So this would also really be something the industry is interested in, and this is why neuromorphic chips are so interested. So now I've hopefully convinced you that this is a cool topic, we should continue, but how can we do that? So how to mimic the brain? To answer that question, we first have to look at what the brain is really doing. And I'm not an expert, so I share only the basics. So I hopefully you're not asking me any neurology questions. But what is the brain doing? So we have neurons, you all know that. They have dendrites, and they are connected to many, many other neurons. And at the point of connection, you have a synapse. And the information processing is done via an electrical potential. There's usually a static potential, and then if a spike occurs, the potential changes, and then this spike is propagated along these dendrites, the axon, and then it reaches the synapse. So now you would think a spike reaching a synapse would automatically release another spike. No, this depends, because the synapse has a kind of a memory. It depends how, for example, on the timing of the recent spikes, if the synapse decides to spikes or to propagate this spike. So there is a kind of a mixed system there. If you compare it to computer, you have a digital component, because either there is a spike or not a spike, so this is yes or no. But on the other side, the synapse kind of has an analog component, because it remembers the timing and the amount of preceding spikes, and this is related to if it spikes as well. So this is like a capacitor, basically, accumulating the electric charge. So the brain is a mixed signal system. Analog computing in the synapse, but also this binary spiking information. So if we want to build a computer chip who is doing similar things than our brain, there are a few keywords we can keep in mind. In-memory computing, I will come to that in a second. What's the difference to our current systems? Asynchronous logic is also important. Our brain is only doing something if it has to do something. If there's no sensory input, no processing, then there is no spikes, which is energy efficient. If we look at our computers, there is a frequency in there, and they do something in this set frequency. It doesn't matter if there's something to do or not. Connectivity and self-learning. So as you have seen, the neurons, they are connected to so many other neurons. and they can also change the weight of the synapse. So if you know that this is learning. So if you do something a lot of times, then it gets easier. So these connections are then strengthened, and others are weakened. You also know that if you have learned a language in school and then you don't use it, you just forget it. So this is the self-learning and de-learning component, and a lot of these things are happening in parallel. There's a massively parallel computation going on in your brains all the time, even if you are asleep. So these are the elements computer designers are trying to mimic when they go towards neuromorphic. And now let's have this in a very simple way. So current systems, they have memory, they have logic, you know that much better than me as a chemist, and at the moment they are separated. So you have the logic, the processor doing calculation, and then has to talk to the memory, and then the memory gets another operation to the processor, and so forth. So you have a lot of communication between these two units, and because the logic element is getting so fast and potent, we have something which is called a memory wall. So this shuffling the data back and forth is limited. So you cannot do that, you cannot increase the speed unlimitedly. So that's a problem. You also get a heat problem at some point. So what you can do to get these systems more operating like the brain is to use deep learning. So to use the software to that. So software can also work similar like the brain is doing, but then you don't change anything in the physical thing. So you get a higher computing power, you can get artificial intelligence in the way like we have it today, but the energy efficiency is not really amazing. Next step would be just to bring these two elements closer together. This sounds trivial, but obviously it isn't. So maybe computer circuit designers can tell you why. If you bridge the gap, or if it's closer together, then you have less problems with this memory wall. You can increase the computing power, and also the efficiency is a bit better, but it's still limited. And this is then called near memory computing. Here, definitely the chip architecture is the enabling factor. And then what we are interested in, and neuromorphic systems is the last point, you merge memory and processing, like the brain is doing. The synapse is doing the memory and the processing basically in one thing. And this is then a totally different chip component than before, totally different materials. And a keyword here is memristor or memristive elements. So you merge the memory with a resistor. It's not a transistor anymore where you have on or off. It's a resistor where you can have different analog states like the brain is doing. And let's have a look a little bit at the timeline. So artificial intelligence is something we know for, I don't know, what is it, 60, 70 years, so the theory out of it, and then there came a lot of algorithm milestones, but since 10 years, there are also hardware developments, and maybe we hear later on a little bit about the, no. Okay, also Intel has a very, very nice neuromorphic processor. There are very big platforms like the Brainscale or the Spinnaker out of the Human Brain Project, and they have built platforms trying to understand the brain much better because we don't really know everything about our brain. There are just a little bit of information we are trying to translate into hardware. And we in Merck, we have a strong business in semiconductor materials, and we are convinced that for memristors, you need different materials than today, or different processing, or different stack design. And this is where we can add, and this is where we currently are looking for projects, looking for contribution, how we can advance that field to make edge computing possible and to reduce in the end, the energy footprint of our digital systems. So before I now close, I also want to end with a personal note. So I just moved my flat, and when I unpacked my boxes, I found the Abi-Zeitung, so the paper we have done when we graduated from high school. And in that paper, really funny style, so every pupil has a short text about himself or herself written by the friends or also partly by yourself, and it was really amusing for me to see what my friends wrote about my 18-year-old self and also what I wrote. And there was one part about it saying, what do you want to do in future? So, and I read that and I said, okay, part of that is still true. Still true is that I wanted to do something with chemistry and sustainability. So I basically managed to do that most of my career life, and still with neuromorphic systems, chemistry is important, sustainability is there, okay. So that's still the case. But the other things, they were like standard things, like have a great career, have a family, have a house, all these things. And then I was thinking like, okay, what did I mean when I wrote that, 18 years old? And I realized, so at that time, and also then some years after that, I just took on what I got from my parents, which is, I think, quite natural. So I thought it's important to have a strong career, it's to earn a lot of money, to have a big group, to have a vice president level at some point. So, okay, and then during my PhD, at some point, I start reflecting. I start like, is it what I want? Why would I want that? A lot of money, a lot of people. And I started to define what means successful for me. And I think this is a very important question. And it might sound trivial if you already have a clear answer to that, but at the point of my high school graduation and also my studies, I wouldn't have an answer which would be my personal one. I would have the standard answer. And I think there is no good or bad answer to that, but you should, I think everybody should reflect, what does successful mean? So for me, yeah, of course, a certain level of money is relevant, because otherwise you really have issues, but it doesn't really matter. Above this level, it doesn't really matter. For me, it's important to make an impact and to have a purpose in what I do. Can be neuromorphic systems, but also outside of my life, outside of my work life. So I've decided 3 years ago to reduce my paid job, to have more time for other things I do. Which is, I'm interested in neuroscience, which is now also fitting to this topic. So I'm working now mainly 4 days a week, and if you're interested how this works, no problem. So I have never ever occurred any negative feedback to that. So if you want to do that, just try it and see what happens. To do part-time, also without small kids around. Yeah, so I think the question, what does successful mean for you? And maybe even a much harder question, what would I do if I would not need to work for money? This is a question I don't yet have an answer for. So it's a really hard question because we're not used to ask ourselves these questions. So maybe you want to think about these questions and also refresh your thinking about that from time to time. And with that, we can continue that discussion over the break, and thank you for your attention.
So I think you made the vice president of Merck very insecure now, because
there are many vice presidents at Merck.
Okay, maybe all of them. Do you have the ambition to become vice president? Any questions? The gentleman was faster than all other ladies.
So my question was with the neurons and stuff like that. Do you later need like a neurologist to analyze what it does, or seeing as those things are still like a black box for us and we don't fully understand the human mind completely yet? How do we make sure that it does what we want it to do? Like, sure, if we take like AI models and we apply it for this to emulate those things, it'll do that. But if we go beyond that, I wonder how, like, can you analyze that already, or? So it really depends what you want to do. So what we would like to do is to develop a chip or chip component which has a stronger computing power while using less energy. So to solve that question, I think the information which is out there is enough to tackle it. But to really understand our brain and to fully mimic that, there's a lot of unknown things. And for that, disciplines really need to come together. So you really need the neuroscientists and the informatic people and mathematics. So different communities coming together, and this is also happening at the academic world mainly. So it really depends what question you want to solve. For example, these platforms like BrainScales and Spinnaker, so they really have the major task to have a computer system which is more able to mimic what our brain is doing, so really replicating hundreds and millions of neurons and synapses to get a better understanding about the processes. But they are not focused mainly on getting a more intelligent smartphone, for example. So these are just different areas in this very wide field, and yeah. It's a multidisciplinary approach.
Okay. Any other question? I saw some hands. Change your mind? Okay. So this is also a present for you. Now that you have more
Thank you very
time, you
much.
can always look at it and think about us.
Time is always filling
Okay.
everything. So.
Okay, but what she said about time, it doesn't work for PhD students. They must work 7 days, 24 hours a day. Okay, so
At least yours, huh?
thanks a lot, please.